Hello and welcome to the Maths 2 component of the online BSc program on data science. In this video, we are going to study the notion of the image and kernel of linear transformations. So, remember previously that we have studied the notion of the null space. So, this is some for a matrix. So, this is some analogous thing for a linear transformation. So, for a matrix we know what is the row space or the column space, and that is the analogous notion for a linear transformation is the image. So, let us start by the from the definitions. So, let f v to w be a linear transformation and define the kernel of f, which is denoted by ker, ker of f, as kernel of f is all those vectors v such that f of v is 0. So, v and w are vector spaces, f is a linear transformation and we are looking at all those vectors so that f of v is 0. Now, it is easy to check that kernel of v, kernel of f is actually a subspace of V, which means it is a vector space in its own right. What that means is, if you take a linear combination of elements of kernel of V, they still belong to kernel of V. Okay, define the image of f. This is denoted by Im of f. Sometimes we will use a little I and sometimes we will use capital I. So, that may that notation will be a bit vague. So, we will define it as all those vectors w, so that there exists v in V, so that w is equal to f of v. So, this is nothing but the usual definition of the range of a function, right. If you have a function between two spaces or two sets, we call the range of f as the set of values which the function takes, right. So, that this is exactly the range of the function. So, image of f is another name for the range of the function f. And I think you have studied range of a function in maths 1. In case you have not, I will just recall for you that range of a function is the set of values which the function f takes. Okay. So, anyway, if you did not follow what I just said, we will anyway look at some examples. Okay. Before that, let me also comment on the previous slide that the image of f is also a subspace of w. So, if two vectors are in the image, the sum is also in the image, because you can take so if w1 is f of v1 and w2 is f of v2, then you can look at f of v1 plus v2, that is exactly w1 plus w2, because remember f is a linear transformation, and that means w1 plus w2 is also in the image. Similarly, if you have alpha times w, where w is in the image, then w is f of v. So, you look at alpha times v, then f of alpha v is alpha times f of v is alpha times w. So, alpha w is also in the image. Both of these, remember, use, in the proofs that I gave, the statements that I just made, the fact that it is a linear transformation was crucially used. So, this is not true for functions and so on, for other things. Okay. So, let us look at some examples to get our ideas straight. So, look at the function from R2 to R2, f of x y is 2x comma y. First of all, why is this a linear transformation? Because each coordinate is a linear combination. Remember that linear combinations, if each coordinate is a linear combination, that is exactly what a linear transformation is when it comes to functions from Rn to Rm. So, 2x is a linear transformation of x and y is a linear transformation of x and y. So, this is indeed a linear transformation. So, each of these are linear combinations. So, this is a linear transformation. Okay. So, what is the kernel of f? The kernel of f is all those values, so that f of that number x comma that vector x comma y is 0. 0 where? 0 in the codomain R2. So, 0 in the vector space R2. So, 0 in R2 is 0 comma 0. So, in the previous slide also note that we said f of v is equal to 0. By that 0 we mean the 0 in w. Okay. So, here we have we want to look for those x y such that f of x y is equal to 0 comma 0. So, it is clear that if 2x comma y is 0 comma 0, then 2x is 0 and y is 0, which will tell us that x is 0 and y is 0. So, the kernel is exactly 0 comma 0. So, the kernel is the 0 element or the 0 vector in R2. Okay. What is the image of f? The image of f is the entire R2. Why is that? So, if you want to write a vector w in R2 as the image of some element, then what would you do? You would look at suppose w is equal to u comma v, then you look at u by 2 comma v, and if you apply f on u by 2 comma v, you get 2 times u by 2, which is u, and v. So, that tells us that u comma v is in the image. So, every vector u comma v is in the image, that means the image is the entire space R 2, the entire vector space. Okay, consider the example R 2 to R 2, f of x y is 2 x comma 0. Again, this is a linear transformation because each coordinate is a linear combination. So, what is the image and what is the kernel? So, kernel of f is 0 comma y. Why is this? Suppose f of x y is equal to 0, we want to, from there we want to solve for x comma y. So, that means 2 x comma 0 is equal to 0 comma 0. That means 2 x is 0 and 0 is equal to 0. So, 0 does not yield us any anything on x comma y, any restriction on x comma y. 2 x equals 0 yields us the restriction x is equal to 0. That means y can be anything, right. So, the kernel of f is 0 comma y. So, this is the entire y axis, right. 0 comma y is the y axis. Okay, and what is the image of f? Image of f is well, you have f of x comma y is 2 x comma 0. So, now suppose you look for an element u comma v and you ask when can u comma v be equal to 2 x comma 0. So, the first thing you need is that v is 0. That means, this element must, this vector must lie on the x axis, and then we have to ask whether on the x axis it can take all possible values. So, you get the equation u is 2 x, which if you solve you get x is u by 2, which means if you put x comma y equal to u by 2 comma 0, then the image of that element f of x comma y is u comma 0. So, you get that every element, every vector on the x axis is indeed in the image, and we already saw that the image is contained in the x axis. That means, the image is equal to the x axis. Okay. So, let us go on to studying the relation between the kernel and injectivity, which, so remember that a function or a function is injective or 1 1 if f of v 1 is equal to f of v 2 implies v 1 is equal to v 2, and for linear transformations this is the same as demanding that f of v 0 implies v is 0. Yeah, we proved this actually. So, what does this have to do with the kernel? Well, the first one you may not be, it may not be clear, but the second statement makes it clear what it has to do with the kernel. F of v equals 0 implies v 0. So, if a linear transformation is 1 1 or injective, then the kernel must be 0. That is what we are saying, because if f of v is 0, then v must be 0. So, the only possible choices of vectors which yield that f of v is 0 is the 0 vector itself. So, if f is 1 1 or injective, then the kernel of f is 0. On the other hand, if the kernel is 0, that means whenever f of v is 0, v is 0. So, that means the condition for being 1 1 is satisfied. So, kernel of f is 0 also means that the linear transformation is 1 1. So, being the linear transformation being 1 1 is equivalent to kernel of f is 0. That is what we have proved here. So, linear transformation is f is 1 1 if and only if kernel of f is 0. So, what do I mean by kernel of f is 0? What I mean here is that it is a 0 subspace. So, this should be better written as kernel of f is the 0 subspace, which means it consists of the set 0. Yeah, and remember 0 itself is a vector space. It satisfies all the properties of a vector space, and it is a subset of V. So, it is a subspace of V. So, kernel of f is the 0 subspace. That is what we mean by these two statements here. Kernel of f is 0 and kernel of f is 0. Yeah, so be careful when we write this. The 0 in this case here on the right is the 0 subspace and not the 0 vector. Okay, it means it is a set consisting of the 0 vector. Okay, So, let us again see the relation, like kernel is related to being injective. Let us study what is the relation between the image and the surjectivity of a linear transformation. So, recall that a function f v w is onto or surjective if for each w in w there is some v in v such that f of v is w. In other words, the range of this function is the entire w. Okay. So, this is actually, this part is the same for any function. This is not, this has nothing to do with linear transformations per se, what the statement in this slide. So, it follows from the definition that a function f being onto is equivalent to range of f being w. That is exactly what we just commented. So, for linear transformations in particular, this means that, because remember range is the same as image, only thing is when we say range we think of it as a set, and when we say image we think of it as a subspace. This is the main difference, otherwise there is no real difference between range and image as such. So, a linear transformation is onto if and only if image of f is w, and this image of f is w is being concluded as a subspace. Image of f is actually a subspace of w always, and we say that it is onto, we have proved that it is onto is equivalent to the subspace image of f actually being the entire space. Okay. But this is not very different from what happens for functions. Okay. Let us now proceed and make the connection between kernels and null spaces. So far there is no matrix in the picture, right. So, now we are going to introduce some matrix in the picture, and we will associate the kernel of this linear transformation with that matrix. So, let f v to w be a linear transformation, let beta be v 1 v 2 v n and gamma be w 1 w 2 w n, which are both of which are ordered basis. Beta is an ordered basis for v and gamma is an ordered basis for w. So, now indeed we can talk about a matrix, because remember in the previous video we have talked about how if you have a linear transformation along with an ordered basis for each of v and w, there is a corresponding matrix. And how do we write down that matrix? We write down that matrix by looking at f of v I and expressing that in terms of the wj's as a linear combination of the wj's, and whatever coefficients we get go into the matrix. So, the coefficients of f of v I go into the ith column of that matrix. So, let A be the corresponding matrix. So, just recall that for v in, so suppose v is summation c j v j, then f of v is equal to summation c j f of v j, that is by the linear transformation property, axioms of being a linear transformation. And then f of, so summation f of v j can be further written as summation a I j w I. Okay. So, f of v j is summation a I j w I, right. So, that is corresponding the jth column of the matrix A. That is what these where these coefficients are coming from. That is exactly what we just commented. Okay. So, when is f of v equal to 0? Yeah. So, f of v is 0 if and only if each coefficient in this linear combination of w i's is 0. So, what is the coefficient of w I? So, you have to take that summation I is equal to 1 to m outside and take the summation j is equal to 1 to n inside, and then you will get summation a I j c j over j, that is the coefficient of w I. And then we know that if you have a linear combination of w i's which is 0, then each coefficient must be 0. Why is that? Because w i's are a basis, remember, and basis satisfies that it is linearly independent. So, if summation of some linear combination, this particular linear combination of w i's is 0, then each coefficient is 0. So, f of v 0 is exactly the same as saying that summation aij cj is equal to 0. Okay. And now this equation should ring a bell in your mind. So, the left hand side is saying, so f of v is 0 means this is exactly the definition of v being in the kernel of f, and the right hand side is saying that if you look at the vector c consisting of c1, c2, cn, then that vector is in the null space of A. Okay. So, the relation we have between the kernel and the null space is the following, that if you have a vector v which when you express as a linear combination of the vj's, there remember that it is an ordered basis. So, you can write it as summation cj vj in a unique way. So, this vector is in the kernel if and only if this happens precisely when, if you write these coefficients of the vj's as a column, then this column must be in the null space of the matrix A. So, that is the relation between kernels and null spaces. Okay. So, let us similarly describe what is the relation between images and column spaces. So, let V be a f v to be w be a linear transformation, let beta be v1 v2 vn, gamma be w1 w2 wn, both of these are ordered basis, beta for v and gamma for w, and let A be the matrix corresponding to f with respect to beta and gamma. So, we know how to write this. The jth column of A corresponds to the coefficients arising as expressing f of vj in terms of wi's. So, now again recall that for v is summation vj w cj vj and v, f of v is summation cj summation aij wi, which if you take the summations, interchange the summations, we can do that because it is a finite sum. Then you get that this is summation I is 1 through m summation cj summation aij cj times wi. So, the coefficient of wi is summation aij cj over j. So, suppose now w is summation di wi, and it's so this is a vector in w. So, these di's are unique because w is a wi's form of basis. So, you can write w as summation di wi. So, when does this lie in the image, right? So, this lies in the image precisely when there exist scalars cj, so that summation aij cj is di, right. So, the scalars from the coefficients of something in the image, something of the form f of v is summation aij cj. So, that means these d I should be summation aij cj in order for w to be f of v, where what is v? V is equal to summation cj vj. So, what that means is, we can now express this in terms of columns. What it means is that summation di wi is an image of f. If there exists a column vector c such that the column vector d, which is d1 d2 dm, is equal to a times c. Excuse me. So, but remember a times c is exactly a linear combination of the columns of A. So, what that means is that w is in the image of f, where w is given by summation di wi, if and only if you look at the vector d is equal to d1 d2 dm, and this is in the column space of A. Okay. So, that is the relation between the image of f and the column space of this matrix A. Now, let us see if we can use this to find the basis of the kernel and the image of a linear transformation. So, again let f v to w be a linear transformation, choose ordered basis beta and gamma for v and w respectively, let A be the corresponding matrix. Okay. So, the point the first point here is that we can look at the kernel and the null space, and what we have really shown is that the kernel is isomorphic to the null space. That is what really we showed in the slide on kernels and null spaces. Why is that? That is because for every element of the kernel, we have a unique element of the null space. So, you can define a function, and it is easy to verify that this is indeed a linear transformation from the kernel to the null space, and it is also equally clear that this function is both 1 1 and on 2, that is something you can check. So, that tells us that the kernel is actually isomorphic to the null space. So, in particular, if you look at the vectors C11, C12, C1n, C21, C22, C2n and Ck1, Ck2, Ckn, these form a basis for the null space of A precisely when V1, the corresponding V1 primes, V2 primes, Vk primes lie in kernel of F, form a basis for kernel of F. And what is the relation between Vi's and Vi primes and these columns? The coefficients of Vi prime when expressed in terms of Vj are exactly corresponding to the jth the ith vector in this collection. Okay. So, in other words, what is the main point? The main point is I can read off a basis for the kernel if I know how to get a basis for the null space, and indeed we do know how to get a basis for the null space. Similar to the previous situation, we can find the relation between images and column spaces, specifically about basis between them using the isomorphism that we have discussed earlier. So, if we consider the column vectors d11, d12, d1m, d21, d22, d2m, dr1, dr2, drm, then these form a basis for the column space of A precisely when, if you look at the corresponding linear combinations of the Wi's, Wi prime is summation j is 1 through m dij wj, these form a basis for image of F. So, this follows because of the previous isomorphism that was discussed. So, once we have this isomorphism, note also that if you look at the columns of A which form a spanning set of the column space, then these correspond to the images of f of Vi. So, the images f of Vi which form a spanning set for image of F. So, what is the point of all this? So, as we have noted before, we can convert the problem of finding a basis for the image space to the problem of finding a basis for the column space, and well, that is something we know how to do, because to find a basis of the column space, what do? We look at the columns, then we do row reduction, and once it is in reduced row echelon form, you look at the columns containing the pivot elements, and then the original columns, those were the ones which form a basis for the column space. So, now what this is telling us is, once we know those columns which form a basis for the column space, you look at the corresponding linear combinations of the Wj's, and that will give you a basis for the image of F. So, this video we have seen the notion of image and kernel, and we have discussed these relationships between the kernel and the null space of the associated matrix once we fix basis, ordered basis, and similarly the relationship between the image of a linear transformation and the column space of a matrix which we obtain by fixing ordered basis. So, we have seen that these are isomorphic, we know the interplay between these two, and using these we can get basis by considering these corresponding matrices that we obtain, and then obtaining basis for those using row reduction, which we know how to do from the last week. So, in the next video we will implement all of this in concrete examples. Thank you.